Hello folks, and welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use concept of equivalent capacitance to simplify a circuit down, and how to analyze the end circuit, and to go back and analyze the original circuit after you get the thing simplified down. So in this example, what we're looking at here, we've got a 12-volt battery hooked to a switch and a bunch of capacitors that I have labeled C1, C2, C3, C4. All with values that I've kind of written over here on the left. So we got a 12-volt battery, a 2 microfarad capacitor, etc. Now just remember, a capacitor, or a farad means a coulomb per volt. Keep that in mind when working this problem. Okay, so now let's talk about just conceptually what happens when the switch is closed here. So if we close the switch in the circuit, the battery will now push charge through this system. So what we're going to end up with is we're going to end up with a charge configuration that's going to look like this. Go through and put all my pluses and minuses. Right? And the reason for that is this positive terminal of the battery will draw electrons, and this negative terminal of the battery will basically push electrons away. So there's going to be kind of a charge shift. And we're going to draw electrons from this plate, leaving it positively charged. We're going to be pushing electrons from this part of the battery into this part of the circuit, negatively charging all of these. So this is the charge configuration we're going to end up with. Now, we're going to have different charges on all of these things here. So I'm going to give them names here like Q1, Q2 for the charge on this capacitor, Q3 for the charge on this animal, Q4 for the charge on this animal. And we're going to go through and talk about how to calculate all those charges here. But before we do that, I want to talk about potential difference and how it relates to the circuit now. All right? So it's important to notice that, remember, conductors themselves are equipotentials. So I always like to go through it in any of these problems, and I like to go through and kind of color code my potentials here. So this represents a terminal of the battery. This is all conducting material because, this is a wire or something. So that would all be one potential up to that point. Right? Now, potential will change across a capacitor because, typically they're filled with a dielectric material, or, maybe it's just air in there, usually not. But anyway, this is not conducting material between them, so we're going to have a potential difference across the plate here. So we're going to be at a new potential now. I'm going to go ahead and, let's see, use orange for that one. Right? So this is all going to be one potential. And again, this is all constant because this is conducting material. All right? Now, across these capacitors, we're going to get another drop in potential. I'm going to go ahead and use, actually, to tell you the truth, this is all black. I'll just leave this black. That's all one color. That's good enough. So as we kind of look at our circuit here, again, and you look at the potential differences, we have red to black, which is a 12-volt potential difference, red to orange, which we don't know the potential drop across that yet, and then orange to black. Right? Now, the idea here is to take this complex circuit and try to simplify it down into a simpler circuit. These guys here are all in parallel. And let me talk a little bit about this connection point. Pardon me. Now, again, this is all black, so this is all one potential. Where this thing is connected doesn't matter in this problem. If I were to cut this wire and move it over to, make it the same color wire, and move it over to here, it's exactly the same problem. Or in fact, I could connect this wire to here, and it would be exactly the same problem. Where that wire's connected does not affect the problem at all. So I'm just going to go ahead and connect it here again. All right, and that's, the reason it doesn't affect it. This is all one potential here, so it does not matter where this wire is connected. These guys are all in parallel, as long as this wire is connected somewhere in this region. Now, these guys right here, all in parallel, so the equivalent capacitance is very easy to find. Oops, let me do this down a little lower here. So for that combination, C equivalent is going to be the sum of the capacitances of these capacitors. So that's going to be C2 plus C3 plus C4. And if we go ahead and just add these up here, that's going to be 1 microfarad plus 3 microfarads plus 5 microfarads. So what we're going to end up with is a capacitance of 9 microfarads. Now, I don't need this work anymore, so I'm just going to get rid of this because I got to save myself some room here. All right, so what we know is that the equivalent capacitance of this combination is 9 microfarads. So I'm going to go ahead now and redraw the circuit. Right, here's my C1. And in the place of all of this stuff, I'm going to go ahead and put a 9 microfarad capacitor, because that's what we just calculated, a capacitor that would be equivalent to that, to the C2, C3, and C4 in parallel. Right, so now our system looks like this. And I'm going to go ahead and make sure and get the voltages in. So this is my red voltage to here. See if I get that same orange here. All right, this is my orange. Oops, that's a little bit. Yeah, that's good enough. That's close enough. All right, there's my orange potential, and then there's black. And again, our charges are looking like this. Right, the charge on this is I'm going to call C1 here. There's a charge on this that I'm going to call let me back up. C1. Q1 is the charge on this capacitor, and then I'm just going to call the charge on this capacitor Q. And that's an unknown value as of right now. Now, this combination now is a series combination. So what we can do here is we can simplify that down one more time by saying this: 1 over C equivalent is going to equal 1 over C1. Now I'm going to looking to the left here. C1 is 2 microfarads plus 1 over this capacitance, 9 microfarads. And if we go through and we calculate C equivalent for this, what I get is 1.64 microfarads. And the 1.64 microfarads is equivalent to this pair in series. So what you do when you're calculating this, just take your calculator and go 1 over 2. Just leave the micro out, treat it like a unit. Just go 1 over 2 plus 1 over 9, hit equals, and then invert your answer, or raise it to the -1, and out will come 1.64. And then I'm just tacking the micro along with the farads. So this means now we can redraw our circuit again. And I strongly recommend, whether you're dealing with a capacitive type system or a series of resistors, that whenever you find an equivalent, you redraw the circuit. So I know it seems like it's kind of a waste of time or a waste of paper, but it's not. It's very important that you have all these pictures so that you can work from our end result here back to the original diagram. All right, so in this picture here, this is the voltage of the battery here. Again, that's 12 volts, and this is plus, minus over here, plus, minus. All right, the capacitance of this capacitor, 1.64 microfarads. It has some charge on it that right now I'm going to call unknown. All right, so what I've done so far is I have simplified the circuit down from this, kind of messy looking thing down to a single capacitor. And what this means is that as far as the battery is concerned, it really couldn't tell the difference between whether it was hooked to this combination or hooked to this single capacitor with a value of 1.64 microfarads. All right, now we're going to start working the problem backwards. We're going to find the charge on that capacitor, and we're going to use that to find charges over here and voltages, and then we're going to come back to the original picture. So capacitance, remember, is charge per unit voltage. So what we can say is that the charge on any capacitor is equal to capacitance times voltage. So looking at this capacitor right here, we can say that the charge on it is going to be the capacitance, 1.64. Let's see, that's going to be microfarads. Keep in mind a farad is a coulomb per volt, times the voltage on that capacitor. Now here's the nice thing about having this color-coded. As I look here, red to black here means 12-volt potential. And on this capacitor, that is red to black. So the potential across it is 12 volts. So we go ahead and calculate a value here for the charge. I get 19.68, I'm just going to round that to 19.7 microcoulombs. So this charge now not unknown, that's now a known value. So the charge on that capacitor, let's see again, 19.7 microcoulombs. Again, remember that this guy right here is a coulomb per volt. So when we take a coulomb per volt times volt, these cancel and we're just left with microcoulombs. Right? Now, we're going to talk about how this relates to our previous pictures. So look at the middle picture here. And again, this is a single loop, and it's very important to realize how charge moves through a system, a wire like this. If 1 coulomb of charge moves across that point, 1 coulomb has to move through here, 1 coulomb has to move through here, 1 coulomb has to move through here. The exact same amount of charge has to move through all points in the system. So what that tells us is this. If this is 19.6 microcoulombs, then the charge here is 19.6 microcoulombs, and here, 19.6 microcoulombs. So we now know the charge on both of these capacitors. Right? Next step, right? If I take a look at one of these capacitors, let's say this one, and I write this out, we know that capacitance is equal to charge over voltage, and I take note of, I know the capacitance and the charge on it, we should be able to calculate the voltage on it. The voltage should equal charge divided by capacitance. So again, and I'm focusing on this guy right here right now. The charge on it we just found to be 19.6 19.6 microcoulombs divided by the capacitance, which is 9 microfarads, and you notice the micros divide out. The voltage across that guy is 19.6 divided by 9, basically 2.18, or let's just round that to 2.2. We're going to call this about 2.2 volts. That's going to be the voltage across that capacitor. Now, we can calculate the voltage on this capacitor similar, right? So this guy right here. The voltage across it is going to equal the charge, 19.6 microcoulombs, divided by the capacitance, C1, 2 microfarads. Right, so let's see, 19.6 over 2 here. Okay, we about 9.8 volts across this. So now we know the voltage and charge on both of these capacitors. I'm going to take a little note here that when we add these, 9.8 and 2.2, they're adding to about 12, and they should. Notice we're going from red to black, and the red to black is a 12-volt potential. All right, let me get rid of this now. Now we have to work back to our original picture. And in our original picture, if I look at this guy, C1, Q1, and the voltage is red to orange there. And the Q1, the C1 we know, the Q1 we've already calculated, and the voltage across it we know is 9.8 volts. So we're basically done with that capacitor. There's really nothing to do there. Some stuff we have to do now is we have to relate this one to these. And this charge, 19.6 microcoulombs, right, that's not equal to the charge on each of one of these. We've got Q2 here on this guy, Q3 on this guy, Q4 on this guy. None of them is equal to the 19.6. What I can tell you is they have to add to 19.6. I'm going to go ahead and write that out, that Q2 plus Q3 plus Q4 does have to add to the charge on that capacitor. 19.6 microcoulombs, right? But to actually find the charge, I'm going to use this fact. Orange to black, 2-volt potential. And as I look over here at these capacitors, orange to black, orange to black, orange to black. Right? These capacitors are in parallel, so the voltage on them is the same. So we know the voltage across every one of those capacitors. So I'm going to just take these one at a time, starting with this guy. So since capacitance is charge over voltage, and we know the capacitance and the voltage, so I'm going to rewrite this Q equals capacitance times voltage. So for this guy right here, we're going to have the capacitance C2, which was 1 microfarad, times the voltage across it, which we know to be the same as this guy, 2.2 volts, and we end up with 2.2 microcoulombs for charge 2. Charge 3 is going to be the capacitance of charge 3 microfarads, times the voltage across it, again 2.2 volts, we get 6.6 microcoulombs. All right, deal with this guy. Q4 is going to be the capacitance Q4. As I look over here, we got 5 microfarads. times the voltage. Again, orange to black, that's 2.2 volts. And what do we get out of that? 11, I think? I think that comes out to be 11 microcoulombs. Right. And I'm just going to do a quick check here and make sure that they add up to my 19.6. So what do we got here? Let's see, 17, 18, 19, 0.6. Well, 0.8, a little high. I suspect what happened is, I've done a little rounding back here and there. These things basically add to 19.6. And again, I did not carry enough sig figs. I did not carry 3 sig figs accurately through all this work. So for all practical purposes, I think these add to 19.8. But that little difference is coming from rounding. I'm reasonably confident. So looking back now at our original problem here, we have the charge and we know the voltage across every one of these capacitors. So again, let me kind of recap how we do that. So you take your original, your kind of complex circuit, and you identify any parallel or series parts in the circuit. So the first thing that jumps at me is this, that this is a parallel combination. So for capacitors in parallel, the equivalent capacitance is just add. So by the time we add this capacitance, this capacitance, this capacitance, bang, out came 9 microfarads. Right? Make sure you redraw the circuit whenever you simplify anything down. Next, we identify this as a series combination, right? So we find the equivalent capacitance by, 1 over C equivalent equals 1 over C1 plus 1 over C2, putting the appropriate values to find C equivalent. Outcomes looks like 1.64 microfarads, right? Oh, along with these pictures, I also highly recommend you color code the potentials. I really like to do that. To me, it helps with visualization, helps show me what potentials are the same and what aren't. You get it down as simple as you can, then you work this problem. Once you get it down to one capacitor, you just write out definition of capacitance here, charge over voltage. You should be able to calculate something. The important thing now is being able to backtrack through your pictures. And one of the most, a really important fundamental is this, that, in this circuit right here, if, 1 coulomb moves across that point, 1 has to move across here, here, and here. And in the picture in the middle, that means that 1 coulomb moves through here, 1 has to move through here, 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 all points in the circuit. And what that tells us is that the charge on those capacitors has to be the same. Right, so those capacitors carry the same charge, but not the same voltage. So it's pretty easy to find the voltages using this once you know the charges. Right? Then when we go from our middle picture to the original picture, this is a parallel combination. There's a very important thing to recognize. Yellow to, again, or orange to black, orange to black, orange to black, and I look at this picture, orange to black. That voltage across that capacitor is the same as the voltage across these, right? Voltages are the same for a parallel combination. And that's what allows us to take that voltage and calculate the capacitance on each of these capacitors. So, anyway, that's pretty well it in a nutshell. I hope this video helped demonstrate how to use the concept of equivalent capacitance to simplify a circuit down, a circuit full of capacitors, and then work back to the original to calculate both the charge and voltage across each capacitor. Okay. Have a great day.